Right. Yeah, we'll make a move. Welcome back, everyone. It's good to be back. Yeah, woo. We've got Professor Roulstone with us today. I've messed it up already. It's fine. Roulstone. Ian, he's going to be giving us a talk about kind of the maths behind meteorology. Ian studied mathematical physics at the University of London and then got a DPhil from Oxford, where he was supervised by Roger Penrose and Andrew Hodges. He spent 14 years working at the Met Office before moving to the University of Surrey. Through his career, Ian has written for the Huffington Post. He's worked on TV series, and he's published several books, with Invisible and In the Storm being published in 2013. Just the usual housekeeping. We've got pizza on order for 7. We'll have that in Fizzbar after the talk. We'll be able to mingle, ask questions to Ian, etc. Our next talk is here at 6 p.m. on the 22nd. It's a geophysics career-based talk, so that would be awesome. And yeah, with that, I'll pass off to Ian. Thank you very much.
William, thank you very much. Thanks a lot. And thanks very much for the invitation. It's great to be here. So I'm going to talk about the role of mathematics in weather prediction. I'm also, hopefully, if I make time, going to say something about climate modelling, which I think is, shall we say, a hotter topic these days. And there's a lot of what I have to say is relevant to that problem. And of course, it's a problem that is going to concern a lot of you, probably one way or another, during your careers. So it's always good to know a little bit about the maths behind the models that are making these predictions about future climate. So, the headlines. Mathematics is the language that defines the problem of numerical weather prediction. So this is what we tend to call it, not weather forecasting, numerical weather prediction, because we're using a numerical model to predict the future state of the atmosphere. And we also use these models to predict future climate. Now, mathematics obviously is important in helping us solve the problem. So you write a mathematical model, and I'll give a little bit of background on that, and the maths tells you sort of how to do it. But where mathematics has been really important, and continues to be really important, is not so much in telling you how to solve a problem, but what problem you should try and solve. Because in forecasting the weather, nobody is going to try to predict a sort of turbulent gust of wind that blows up Tyndall Avenue, or something, or a localised storm. You're talking about weather systems with extents of several hundred kilometres, and perhaps more localised effects, say over something the size of the city of Bristol. But to try and predict everything is essentially virtually impossible, and we need to use maths and physics to help us decide what it is that we want to predict. And although this is an ongoing, very active area of research, both in weather forecasting and also in climate modelling, which is now verging on to what we call Earth system modelling. So it's not just modelling future climates in terms of rainfall and temperature. It's how things like the ocean, the biosphere, the cryosphere, the polar caps, and all these things, how they influence the Earth system. And these models have got increasingly complex, increasingly complicated. They can do an awful lot. But in order for us to believe what we see in terms of outputs, we've really got to understand what they're based on. And my talk's going to be more about the basics. The other thing is, big data is a hot topic these days. Everybody's talking about big data science, and, well, it means just about anything, I think. Weather forecasting and climate prediction have been big data science problems for decades, where obviously the notion of big has changed. But as you'll see, you're dealing with petabytes, gigabytes of data all the time in this problem. The question is, can we actually learn something from the science of weather prediction that helps us inform how to use big data in other areas? And I'm going to show you an example of that right at the end. So a bit of shameless advertising. Yes, this is loosely based on my book, co-authored with John Norbury at Oxford, which was published 10 years ago now. And Philip Ball, who was one of the early reviewers, sort of said that one of the things that he liked about the book is it sort of picks apart. It tells you about where things like chaos intervenes and makes it impossible to make a prediction versus actually deciding where chaos is not going to be a problem and you can say things about future weather and climate. And that's going to be central to this talk. Now, I'm going to take a largely historical approach, and really the history behind this subject starts 120 odd years ago with this guy, Wilhelm Bjerknes, who was a physicist, Norwegian, and what he and his father were working on in the 19th century was the hydrodynamics of the ether. Has anybody heard about the ether? Yeah, right. So they thought that electromagnetic waves had to propagate through something, and that you could model things like magnetic interactions through looking at the behaviour of objects immersed in water and set spinning and things like that. So magnetic attraction and repulsion could be modelled by setting sort of spheres rotating in the same direction or opposite directions. And Bjerknes was working on this problem and became quite an expert in hydrodynamics with his father. And then, of course, we got to the point where it was realised that there wasn't an ether, so this is pre-special relativity, pre-quantum mechanics. And so, in some sense, their life's work was almost redundant in that regard. But Bjerknes had, by that time, developed some techniques which he realised could be applied to the problem of weather prediction. Now, in his 1904 paper, which is a very short 3 or 4 page document with no equations in it, he gets right to the heart of the matter, which is one of the key important points to take on board right away about the problem of weather forecasting. And it's spelt out in this short paragraph here. So he says, an exact analytical integration of the system of equations is out of the question. And of course this was before computers were even thought of. Even the computation of the motion of 3 mass points, which influence each other according to a law as simple as Newton, exceeds the limits of today's mathematical analysis. So he knew about what we now know of the non-integrability of the 3-body problem. So Newton's laws of motion, you can find exact solutions for the orbit of, say, the moon about the Earth or the Earth about the sun. But if you try to use Newton's laws to calculate the motion of 3 planets of all similar mass, then finding exact analytical solutions is not an integrable problem. Furthermore, it's a problem that is susceptible to chaotic behaviour. And Bjerknes knew about this. So he knew from the outset that what he was trying to tackle in terms of applying his knowledge of hydrodynamics to modelling the weather was going to be quite a difficult one. And at the very heart of the problem are the equations of fluid motion. This is the equations written down by Euler in 1757 or whenever it was. And this is just Newton's second law for a fluid. So U, V and W are the 3 components of the wind. 2 components in the horizontal, 1 component in the vertical. We're assuming we're calculating the motion of air in something like a room like this, where we're using Cartesian coordinates x, y, z and time t. P is pressure, and rho is the density of the air. And basically this is just forces equal to mass times acceleration for a fluid. But what's really important about these equations is, whilst in principle you want to solve them to calculate the fluid velocity and the distribution of pressure, what you will notice is that those partial derivatives are multiplied by the dependent variables. So u, v and w depend on x, y, z and t, and you'll get terms such as in the first equation, u multiplied by the derivative of u with respect to x. These equations are non-linear, and it's the non-linearity that makes the problem really difficult. And this is before we add in any other physical effects which we will need to do. So what's behind the maths of weather? Well, in some sense, the whole problem can be written down in terms of 7 equations in 7 unknowns. There's one equation for the conservation of mass. Now, if you've done sort of undergraduate particle mechanics, this isn't something that you worry about too much, because you're interested in the motion of billiard balls or something like that. And only under certain circumstances will you consider that ball breaking up into, say, smaller parts. But in a fluid, you need to have a conceptual idea of what it is you're predicting the motion of. Okay, and we use the idea of a fluid parcel. So forces push this fluid parcel around. And you need a mathematical principle that tells you that you can't create or destroy fluid. And that constitutes one equation. There's then an equation of state, the first law of thermodynamics, which relates, there's an equation of state just relating pressure, density, and temperature, Charles's law. There's then Newton's second law for the fluid, so that's 3 equations for the wind speed and direction. And you also have to include the Coriolis effect, because you're solving for a fluid problem on a rotating planet, the Earth. Then there's the first law of thermodynamics, which is the conservation of thermal energy. And finally, there's an equation which tells you about the physics of the total water content of the atmosphere. So your dependent variables are density, pressure, temperature, 3 components of wind speed and direction, and, if you like, humidity or moisture. And all weather forecasts are based, the things that the Met Office does on a daily basis is it integrates these equations from known initial data to create a forecast for the week ahead. That is essentially what's behind it. But this is a highly non-linear, non-trivial problem. And of course, the history goes back to the ideas of buoyancy and hydrostatics, to Archimedes. It was Halley, the astronomer, and Hadley who first used ideas from physics to explain phenomena that they were beginning to observe about global weather patterns. So as people started to travel around the world, trade routes and things like that, they discovered things like the trade winds. And Halley and Hadley were the first people to come up with quantitative theories about why these phenomena exist. And then it was Euler and Bernoulli who formulated the equations for fluid motion. And going on, Boyle and Hooke did some work on ideal gas, and they formulated their famous perfect gas law in the 17th century. Charles then extended that to incorporate variation of temperature, so I'm sure you've heard of all these people. And then in the middle of the 19th century, they were really busy trying to work out what heat was. They thought at first that heat was some sort of substance, and it wasn't until the work of Carnot and Joule and Kelvin that they recognized that it was actually a phenomena related to energy. So all this was needed before you could start thinking about quantifying the problem of weather and how weather changes as a problem in physics. And then we need to take into account the fact that the Coriolis effect, the fact that the winds blow around the Earth is moving, spinning about its axis. We need to incorporate that into the equations as well. So you need a lot of physics before you can even start. But a real breakthrough, and this is where it gets a little bit technical, but bear with me, I'll take you through this. Bjerknes was interested in quantifying the circulation of the fluid, right? So when you pull a plug out of the sink, you get a vortex forming, okay? The bath plug vortex. Now, vorticity is a microscopic measure of fluid rotation. And mathematically, if the fluid velocity is u, vorticity is the curl of that vector field. Okay? U is a vector field because it's got 3 components. The curl of that vector field is known as the vorticity. But you can calculate something that measures fluid rotation on a macroscopic scale, and that's called circulation. And that's defined by this integral C, where you imagine some contour in the fluid, and basically you add up, you integrate round that contour all the contributions to the velocity around that contour. Okay? And that gives you the total circulation about some point. And what Bjerknes wanted to do was he wanted to calculate how circulation changed with time. And he did this for a fluid where pressure can be affected by changes in density and changes in temperature. Okay. So what he did was you can use the equations of motion to convert this integral. When you take a time derivative, as we got here, don't worry about the big d by dt, it's just a time derivative. You want to calculate how c changes with time. You can take that time derivative inside the integral, so you've got an integral of du dt, and then you can use your equations for du dt, Newton's laws of motion, to rearrange that integrand into the form that you get here. And what this is that eventually you get this vector product between two gradients. One is the gradient of pressure, that's G, and the other is the gradient of density, that's K, or 1 upon density. So what it says, what the integral says, where you got B cross G, is it says that the amount that fluid will circulate will change depending on the relative orientation of these vectors. Now, he applied this to the problem of calculating the sea breeze. So what this is showing is, you don't have to look at the diagram, you can just think about this. You're on the coastline on a nice summer's day, right? You're on the beach, sea in front of you, sun comes up, middle of the day. What happens is that land tends to heat up more rapidly than the water. So it starts to get hot over the land, it's cooler over the sea. And what you've got in this diagram is that the dash lines, the horizontal dash lines, are lines or contours of constant pressure. And as we go up in the atmosphere, pressure decreases. Okay? So pressure is decreasing, and G is the vector, it's the gradient of pressure, so that vector G is pointing directly upwards in the direction of decreasing pressure. Okay? If you go back to the other side, there was a minus sign in front of that grad, and that's because G points in direction of decreasing pressure. The solid curved lines, these are lines of constant air density. So air is denser over a colder surface. Cooler air is denser than warmer air. So the air over the ocean will be denser than the air over the land. So typically, these two vectors are not parallel. And if they're not parallel, then that integrand is non-zero, and that means that circulation will change. And what happens is that during the day, once the sun comes up and the land heats up more than the sea, air starts to rise above the land, it draws in cooler air over the sea. As it rises, it returns over the sea and sets up this circulation, which is called the sea breeze. And at night time, things happen in the opposite way. The land cools down more rapidly, the sea stays relatively warm, and the air starts to circulate in the opposite direction. Okay? This is a well-known phenomenon. Now, the key thing here is that Bjerknes worked this out mathematically without having to solve the full equations of motion. He found a way of defining circulation in terms of an integral and could work out how that integral changes in time. All right? So he wasn't tackling, if you like, the full problem. And what he realized is that if he could do this for problems such as this, then maybe you could make statements about large-scale changes in weather using similar principles. So that was really his sort of inspiration. But he realizes that he's still got a very difficult problem. And this is a continuation of the fact that he said, I can't solve the three-body problem, so how can I possibly solve for all the motion of all the points in the atmosphere, which are interrelated by much more complicated equations. So in this statement here, as it comes down to about the third sentence, he says, for to be practical and useful, the solution has to be readily seen, synoptic means over a large scale, so that we omit the countless details which would appear in every exact solution. A weather forecast, a prognosis, therefore, only need deal with averages over sizable distances and over time intervals. For example, from degree of meridian to degree of meridian, and from hour to hour, but not from millimetre to millimetre or from second to second. So at this point, he's realising that if you're going to get anywhere with the problem of weather forecasting, you've got to basically be able to make statements about how large-scale things change quite slowly over large distances. That's about as good as you're ever going to get. And this was, with hindsight, a very profound observation. Now, Bjerknes didn't have, obviously, access to computers, so he'd not only sort of told us what the mathematical and physical problem was, he told us what equations we need to use, but he didn't have any mechanism for solving those equations directly. But he knew there was some hope because he could do things with these sort of contour integrals. However, there was a guy, Lewis Richardson, who actually had a go at trying to solve the problem head-on, but he used the ideas that Bjerknes had referred to. So Richardson was a pacifist, and during the First World War, he refused to take up arms, but he worked as an ambulance driver behind the front lines, rescuing injured soldiers and things like that. And although it's not actually known exactly how long it took him, he spent 4 years in his spare time in the trenches calculating a weather forecast for 6 hours. It took him 4 years to do this calculation. And what this calculation was the following. He happened to have data for the state of the atmosphere over quite a large area of Europe for a certain day back in about 1910, because they'd had this sort of big experiment where they'd flown a lot of balloons, hot air balloons. People had gone up with thermometers and things like that and measured the variation in temperature with altitude, wind speed and direction. So they had this data, and what Richardson realised was that instead of using the equations as we would see them in a textbook, if he could break the equations down into what we call finite difference form, okay, which is where you replace a derivative. So supposing you want to calculate the derivative du by dx, the change in the wind speed in the u direction with respect to the x position. That's an analytical expression, but what you can do to get an approximation is if you know the wind speed over here, you know the wind speed over here, and you know the distance between them, you can subtract one from the other, divide by the distance, and that's an approximation to the derivative. Okay? So what he did was he converted the equations into this finite difference form, used the data, and these squares indicate where he had data from. So the thermometers obviously indicate where he knew what the temperature change was. The arrows with the directions mean where he knew what the wind speed was. And this just wasn't at ground level. It was at 5 levels up through the atmosphere. And his goal was to calculate the rate of change of surface pressure with respect to time in the central square. So you wanted to calculate the derivative of PS with respect to T in the central square. And after working on this for 4 or 5 years, he calculated, his calculation said that the expected change over an interval of 6 hours was about 145 millibars. And in fact, the observation was that the pressure decreased by 1 millibar. Now, if the pressure changed by 145 millibars, our ears would be popping. I mean, that's a dramatic change in pressure. You would never, ever see that. So this was one of the worst, it was one of the worst weather forecasts ever made. Okay? From the point of view of the answer, it was a disaster. But what he constructed is exactly the basis that everybody uses for predicting the weather today. So he found the key to converting the continuous equations into these finite difference equations and using then just arithmetic to solve them. Of course, what he did was, he was a smart guy, he thought, well, gosh, this is horribly wrong, why has it gone wrong? And he continued and found out, he got to the root cause of why his calculation was wrong, and it all comes down effectively to how observational error can be amplified when you're dealing with a nonlinear problem. So you understand why he got it wrong, but he created the method. Now, in the days before computers, what people were really doing is looking at sort of charts of large-scale weather patterns around the globe, and the sort of Bjerknes team, they went on to create this theory of what we call cyclogenesis. So what this diagram is showing in figure A at the top, you basically, sort of north is at the top, south is at the bottom. So if the letter A is sort of closer to the equator, you're looking north. And the dashed line is a boundary between warmer air to the south, colder air to the north. And what this sort of shows is that if something causes that boundary to start to fluctuate, an instability is created, typically the warm air and cold air will wrap round each other in this characteristic pattern, and that is what we recognise today as a cyclone, a large-scale weather system. And this is sort of something that then became known as the sort of classic Bergen model of cyclogenesis, and became very much the sort of benchmark. And you see these patterns in modern satellite imagery. So what you've got on the left there is a satellite image. You've got Spain down in the south, you're over the Bay of Biscay. And what you're seeing is the cloud pattern associated with a cyclone that is approaching the UK. The band of air there is a weather front, and so you basically got warmer, moister air to the right. Behind that, and coming down, if you like, down from the north and behind it, is colder air. So that front will be where you get mainly the wet and windy weather, and then as the front passes, you'll get sort of colder, showery weather coming in behind. So this is what we observe. This is what we observe all the time today, with satellites. But understanding the mechanism that creates these features goes back to Bjerknes and his collaborators in the Bergen School. And this is the point. What you're interested in is trying to forecast the motion of this entire system. You're not really interested in the motion of any one cloud in it. Okay? This is where you need to take this large-scale view. And this is what you can see in forecast charts today. So here, over the North Atlantic, we've got three low-pressure systems wrapping up, and as time evolves, they will move in that northeasterly direction, probably missing the north coast of Scotland, passing between the UK and Iceland. Okay, and this is a sort of characteristic pattern that you see. The continuous lines, the contours are isobars. These are lines of constant surface pressure, and then the lines with the semicircles and the triangles. These are the weather fronts associated with the changing weather type. Now, although we know that sort of motion of the atmosphere is turbulent, it's chaotic, one of the striking things is that if you look at any weather chart, you'll see similar features to this. No two weather charts will ever look identically the same, but you see the same sort of features. What you don't see is something radically different, okay, which is physically possible, but you don't see it. And the reason for that is that the rotation of the Earth, the Coriolis effect, is absolutely crucial to the formation of these cyclones. It's a real controlling mechanism. The other thing that controls what you see, and contrast, say, the atmosphere of the Earth with the atmosphere of, say, Jupiter, the atmosphere of the Earth is actually relatively thin. So the radius of the Earth is about 6,000 kilometres. The depth of the atmosphere where weather occurs is about 10 kilometres. So if you imagine, the atmosphere is like a very thin shell of fluid around the Earth, and the Earth is spinning. And it's this, what we call stratification and rotation, that really controls everything. But again, the challenge is, how do you forecast this sort of thing accurately? Well, the guy who made the real breakthrough in this regard was a guy called Rossby. Now we're turning the clock forward to the 1930s. And Rossby's explanation of the storm tracks is actually very straightforward. So let's go through this carefully. First of all, because the atmosphere is this thin shell, he said, let's imagine the atmosphere is just two-dimensional. It's got no depth, right? I'm just going to treat it as a two-dimensional fluid. Nothing like that exists, but you can write down the equations of motion for a two-dimensional fluid. And then he writes down what the analytical expression for vorticity, okay, which is a measure of the swirl of the fluid, is. So if the fluid's got two components of velocity u and v, vorticity is just the partial derivative of the v component, which is the y component with respect to x, minus the derivative of the u component, the x component with respect to y. That's what measures the rotation of fluid. And if you look at these equations of motion, and this is ignoring any variation in pressure or density, what you can show by manipulating these equations, you can show that the vorticity plus another function is always a constant in this system. And this other function represents the Coriolis effect, right? So let's just move down to this picture here. Imagine you're standing at the North Pole. You're standing still at the North Pole, right? Of course, you're not standing still because you're rotating with a period of 1 day about your local vertical, because the Earth is rotating, so you're rotating with the Earth. So you are spinning about your local vertical axis. If you stand at the equator, you're not spinning about your local vertical axis. You're going round with the equator, but you're no longer actually spinning about your vertical. So the Coriolis effect has this weird effect on things that are moving between the equator and the pole. But what Rossby showed, if you write this down precisely, he says that if I take this function, and let's imagine f is just something, it just varies with sign of latitude. So it's 0 at the equator, it's 1 at the pole. All right? It just varies with sign of latitude. Then he said the Newton's laws of motion for this two-dimensional fluid tell me that if I'm looking at a particular blob of fluid and I'm following the motion of that fluid, wherever that blob is, its vorticity plus the value of f at that point must never change. So if you have, we've got here a hypothetical blob of fluid, a cube, right? A fluid parcel. And it's spinning. It's got some vorticity, which is what a weather system has. So, you know, you saw these cyclones, they're spinning around. So imagine it's spinning, it's moving along, and let's say it's moving from south to a more northerly latitude. Well, if it's doing that, its value of f is changing. So if f is changing with latitude, zeta's got to change so that the sum is constant. So if f increases, zeta's got to decrease. So as it moves north, it spins less. Vorticity has to decrease. What that does, if you again follow the maths through, it means it will change direction. And so it starts heading south again. And so you get this oscillatory behaviour setting up around the globe. And that is largely what weather patterns do. So this is an output from a numerical model of the atmosphere. It's telling us information about the distribution of pressure at a certain level in the atmosphere. And you can see this characteristic wavy motion, which are what we call these Rossby waves. And weather systems typically follow these patterns. And this particular one, which was a forecast from July 2010, over Western Russia, and then indeed over sort of as we move east, you're seeing this characteristic what we call sort of trough and ridge, and weather patterns are effectively following these tracks around the globe, but if this pattern itself is changing, that will influence what local weather is doing. So at this moment in time, it's telling us that there'll be a lot of weather systems moving from the eastern seaboard of the US across the North Atlantic towards the UK, because that's where those lines are drawn. If this whole thing rotates and those lines shift, then our predominant weather patterns will shift. Now, there's a lot of detail here, and a sophisticated computer model created this forecast. But what Rossby showed is that with pen and paper, you can figure out exactly you can predict the existence of these patterns from very simple first principles. And this is what you see on the TV all the time now, where it's related to the jet stream. And weather forecasters like talking about the jet stream. They were talking about it a lot last summer when we got the heat wave, and they were saying, well, this is due to the position of the jet stream relative to the UK. So the things that would bring more changeable weather, the weather fronts, were moving too far north, and we were being basked in warm tropical air for a prolonged period of time. This is all connected with these large-scale patterns that Rossby predicted, and obviously we can now forecast more accurately using sophisticated models. So numerical weather prediction really didn't start until the 1950s, until computers emerged. And what does it involve today? So, in various centres around the world, you have some massive supercomputers. So there's one in Exeter, the Met Office, there's one in Washington, there's one in Paris, Tokyo, etc., etc. And there's a vast global network of various ways of observing the weather that transmit their data several times a day into these centres. So satellites, of course, have global coverage of the Earth's atmosphere, but you can't rely on satellites alone because satellites aren't very good at seeing what's happening underneath a cloud. That's typically where interesting things are happening. Okay? So they can see things at cloud top level. They're not so good at seeing through clouds. But you have commercial aircraft. All commercial aircraft automatically transmit data about weather along their flight path, especially during takeoff and landing, as they're passing through different layers. Commercial shipping do. And then you get balloons sent up, not very big balloons that sort of hang over Montana for several days, but I mean, sometimes these big balloons go off course, don't they? But yeah, if you ignore large Chinese balloons over military sites, you do have weather forecasting balloons that go up, and again, they're collecting data throughout the depth of the atmosphere. So there is a lot of data that is collected on a regular basis, and you're going to need this data together with a knowledge of the physics of the atmosphere to predict what's going to happen next. So what's involved in the physics of the atmosphere? Well, it's not just physics, it's chemistry as well. So a weather prediction model has to represent the effects of incoming solar radiation, how that's reflected by clouds, how some of it is absorbed, how it's absorbed by different types of surface, whether it's the ocean, whether it's the land, whether the land has got vegetation on it or not. All these things are represented in a weather forecasting model. The effects of mountains are significant on global weather patterns. The length of the Earth's day changes depending on prevailing winds over the Rockies and Andes. So prevailing westerly winds over the Rockies and Andes will actually spin the Earth up, and the reverse will happen if the wind is blowing the opposite direction. These things are measurable effects. So you need to represent mountains, obviously. And then there's atmospheric chemistry. And obviously this is very key in terms of the formation of clouds and the interaction of clouds and moisture. So there's a lot of physics and chemistry goes in to these models. But the actual prediction, instead of, this is a modern day representation of what Richardson was trying to do. So at on a grid, so a grid is an imaginary array of points covering the globe. This is at one level, okay, and at each point of the intersection of these lines, you hold data on wind speed and direction, temperature, pressure, water vapour, etc., etc. The grid spacing here is greatly exaggerated. For most global models now, there's a grid point about every 16 kilometres. And then typically there's 137, there's 150 odd levels of these throughout the depth of the atmosphere. Okay? So you can do the arithmetic yourself. You've got basically 7 variables at each grid point and 150 grids nesting around the Earth. So about 10 million unknowns. And you just use the equations you write down and numerical methods devised by Richardson to solve them. That's how it's done. But there's a problem. And that was enunciated by this chap who you probably heard of. After all, your society is called Chaos, so you must have heard of Ed Lorenz. And Lorenz was a meteorologist who, in the 1950s, was working at MIT. And although computers were becoming more widespread in scientific research, in terms of weather forecasting, basically what people felt was the hope for the future was that as more and more data was gathered about weather, the way to forecast the weather effectively would be to say, right, what weather have we got today? And if you want to find out what the weather is tomorrow, you go back in your archive, find when you got a day that was similar to today, look what happened the following day, and that's your weather forecast. Okay? Now, if that is to work, weather has to have some sort of periodicity to it. Patterns must repeat themselves for that strategy to be successful. So what Lorenz was tasked to investigate was periodic behaviour in the weather. Now, he couldn't hope to tackle this problem using any sort of sophisticated model, so he developed a very simple model of weather, and it was actually, again, very closely related to what I've just described, the sea breeze effect. So he wrote down the equations for the motion of a fluid which is heated from below. So this is called convection. So, not surprisingly, it causes rising motion, ascending motion under the heat source, and as you move away from the heat source and things cool down, you get descending motion. It's about as simple as you can get, okay? But it's still described by a set of nonlinear partial differential equations. And Lorenz's stroke of genius was that he truncated these partial differential equations into a set of very simple ordinary differential equations, which is what you've got written down here. So the capital X, Y, and Z are physical unknowns of the system, such as the rate of ascending air, right? And the temperature difference across the domain. The variables sigma and r and beta, which occur here, these are parameters. These are numbers which come from the physics of the problem. So they're fixed. So Lorenz's job was to find functions x, y, and z as functions of t over time. He started with a set of nonlinear partial differential equations. What he ended up with was a set of nonlinear ordinary differential equations, because you get terms in the dependent variables multiplying each other. So this is not a linear system. And he had a computer program that was sufficiently sophisticated and fast that he could use numerical techniques to to integrate these equations. That's what he did. So he makes some particular choice for his parameter values, sigma, r, and beta, and he starts his computer off and he integrates these equations with time, and so you get some distribution of, say, x with time. It doesn't matter too much what the units are, it's just some solution. And, he did this for X, he did this for Y, he did this for Z. And looking at them as functions of time, he didn't really notice any particular pattern, because he was looking for periodicity. He wanted to see if there was some recurring behaviour. Well, then what he did was he decided, instead of plotting each individual variable against time, he decided to plot one variable against another. So now, as time progresses, you move around this green curve. Okay? So as time evolves, you move through different values of x relative to y. You can do it for 2 variables, you can do it for 3 variables. Okay, so we could now plot these three variables against each other, and we call this a sort of state space picture, because each point in that cube is a possible value of your 3 variables, and if you like, your weather forecast is one particular trajectory which tells you how these 3 variables change with time. And it was through this that he discovered chaos. So going back to just looking at a time series of one variable against another, this is the x variable, now plotted over a long period of time, you see this apparently random behaviour, these random fluctuations. There's no real structure in that at all. And similarly with the other variables. But if you now plot those 3 variables against each other in this state space, something rather remarkable occurs. It turns out that your 3 variables all move around a restricted part of phase space known as the attractor in a rather special way. Okay? So the way of thinking about this, or what I want you to do now is to think about this as a weather forecast. Think about one of those disks as representing cold weather and the other disk as representing warm weather. Then what happens is your forecast starts off and it revolves around just one of them for a while, and then it flips over and revolves around the other one for a while. So the weather's changing from warm to cold and back again. Okay? Furthermore, this picture typically only resides in a portion. It doesn't occupy the whole cube. So what you never see is a picture where the whole cube gets randomly filled with lines. They tend to stick to these rather lobed-like distributions, patterns, okay? Now, the point is that whilst this might suggest there's periodicity in weather, it's a little bit more subtle. So what Lorenz was doing as part of his routine experiments, he wanted to make sure, it was the early days of computer modelling, he wanted to make sure what he was doing, his results were robust. So he wanted to check his calculations. So what he did was his computer was working to something like 8 decimal places. So it was producing these numbers to 8 digits of accuracy over the time of the integration. And he wanted to make sure that if he repeated the calculation, he'd get the same results. So there wasn't a bug in the program. But instead of entering the digits to 8 significant figures, he was a bit tired, so he only entered them to 3 significant figures. So to one part in 10,000. Now what this plot shows is that if you do that, he's actually running two integrations here, just looking at the x variable. So under this blue curve, there are actually two curves. And it started by one integration is entering the initial data to 8 significant figures, the other one to only 3. And up to about the point 24, you can't actually tell any difference. And then from time point 24 onwards, all of a sudden these curves separate. So that very tiny difference in the initial conditions suddenly starts to manifest itself in a completely different solution at some later time. And the implication for this for weather forecasting is the following, is that unless you know your initial conditions with a very high degree of accuracy, you could be in a situation where a small error amplifies to a very different forecast further down the line. And this leads to unpredictability. So what you've got on these three plots here is, on the left-hand side, you've got a little black circle on the attractor in some region of this state space. So what you're doing is you're thinking of your possible initial conditions for a forecast as lying within that black circle. And then as time progresses, all these states evolve, and in this case, on the left-hand case, they all evolve in a similar sort of way. They cross over to the other lobe. This little circle sort of elongates, but it remains a sort of coherent circle. And that means that all these possible initial conditions you could have chosen roughly lead to the same forecast. In the middle, you find that to begin with, they look similar, but then some go one way, some go the other way. Okay? So your ability to predict the difference between hot and cold is more limited. And then when you get onto the right, and you start it down there, within a short time, relatively, the whole system becomes rapidly unpredictable. And this is something you have to work with in terms of forecasting. And so what forecasters do is nowadays you don't just run one forecast. So the Met Office run about 50 forecasts simultaneously, all starting from very slight initial conditions. And there's various ways of representing this, but this is the forecast of Hurricane Sandy, which struck the eastern seaboard of US around New York, New Jersey. This was back in 2012. And it's a classical subtropical hurricane, so it starts down in the Caribbean. And what you've got here, each one of these lines is a forecast for the evolution of that hurricane. Now, most hurricanes, when they start down in the Caribbean, tend to fairly quickly, they might clip Florida, but they move out into the Atlantic, and as they move north, they decrease in strength because they're moving north, and their vorticity gets weaker because of this effect that Rossby discovered, amongst other things. But in this case, something very weird was happening, and it was showing this northerly motion and then turned to the left towards the eastern seaboard of the US. So when forecasters see this, they're sort of saying, hey, most of our forecasts are indicating that in 6 days' time, there's going to be a major storm hitting the US. Okay? Had those trajectories gone out into the Atlantic, they'd be saying, no, this is not going to be a danger. And this is how you have to... So you're no longer relying on one one number saying yes or no. It's about it's the balance of probabilities, whether something dangerous is going to happen or whether it's not. And this is called ensemble forecasting. A whole ensemble of forecasts are run so that you can test your own uncertainty in the initial conditions. And just quickly, one of the rather remarkable things about this little box, D minus 8.5, this is something that a numerical model produces on a regular basis. So this model forecasts the weather out to about 15 days. And before this hurricane had even formed, so there was no hurricane, this model started to show something indicated by the green blob, something rather unusual happening in terms of weather patterns over that region of the US 2 days before this hurricane even formed. So it was actually picking up, the observations were sort of saying, hey, the atmosphere is getting into a state where something big is going to kick off before it even did. So this sort of concentrated minds, and people obviously followed the progress of this very carefully. And early warning save lives. So I'm running out of time, but I do want to say a few things about climate prediction. So what I've just said is that weather forecasting for an indefinite period into the future is effectively impossible, because chaos at some point will render your predictions more or less useless. If we want to predict the climate 100 years from now, how on earth can we possibly do that because of chaotic behaviour? Okay? So, of course, this is the usual thing that people like to wheel out, is if you can't forecast the weather for more than a week ahead, you can't predict the climate.